Imagine we are planning a hiking trip, and are interested in bringing some items along with us. We are planning to fill a knapsack with items that are considered necessary for the trip. There are n different item types that are deemed desirable. First, a bottle of water, an apple, first aid kit, a sandwich, and a tent. Each item type has a given set of two attributes, a weight and a value that quantifies the level of importance associated with each unit of that type of item. Since the knapsack has a limited weight capacity, the problem of interest is to figure out how to load the knapsack with a combination of units of the specified types of items that yields the greatest total value. What we have just described is called the knapsack problem. 0/1 knapsack is a combinatorial optimization problem and arises in resource allocation where the individuals have to choose from a set of non-divisible projects or tasks under a fixed budget or time constraint, respectively. The knapsack problem has been studied for more than a century, with early work dating as far back as 1897. The name, knapsack problem, dates back to the early works of the mathematician Tobias Dantzig, 1884 to 1956, and refers to the commonplace problem of packing the most valuable or useful items without overloading the luggage. The decision version of the 0/1 knapsack problem is an NP-complete problem. Dynamic programming is an algorithmic paradigm that solves a given complex problem by breaking it into subproblems and stores the results of subproblems to avoid computing the same results again. Following are the two main properties of a problem that suggests that the given problem can be solved using dynamic programming. There are two different ways to store the values so that the values of a subproblem can be reused. Here, we'll discuss two patterns of solving dynamic programming DP problem. Tabulation, which is bottom-up. Memoization, which is top-down. We can solve the 0/1 knapsack problem. 1. Using recursion by brute force algorithm or exhaustive search. A simple solution is to consider all subsets of items and calculate the total weight and value of all subsets. Consider the only subsets whose total weight is smaller than W from all such subsets, pick the maximum value subset. Time complexity is big O of 2 raised to power n. As there are redundant subproblems. Space complexity is big O of 1. As no extra data structure has been used for storing values. R2. Dynamic programming method where n is the number of weight elements and W is capacity. Space complexity is big O of n times W. The use of 2D array of size n times W. 0/1 knapsack problem has the following restriction on how the item should be picked. Items are not divisible. In other words, you either take an item or not. The first step in dynamic programming is to define the subproblems. In this problem, we can try to label the items from 1 to n, and then a subproblem is to find an optimal solution for S of I equals items labeled 1, 2 through I. Once we have a definition for the subproblem, we need to ask, can we describe the final solution that is Sn in terms of subproblems that is S of I? Let's take a look at an example. Suppose W equals 20, then for S4, the optimal solution is to put item 1, 2, 3, 4 into knapsack because the total weight is 2 plus 3 plus 4 plus 5 equals 14, which is less than 20 and we have the maximum benefit 20. For S5, the optimal solution is to put item 1, 3, 4, 5 into knapsack with the total weight 2 plus 4 plus 5 plus 9 equals 20 and maximum benefit 26. However, as you can see, the solution for S4 that is 1, 2, 3, 4, is not part of the solution for S5 that is 1, 3, 4, 5. Thus, our definition of subproblem is not right. Let's refine our subproblem definition by adding another parameter W that represents the exact weight for each subset of items. Then, our subproblem is to find the best subset of S of I that has total weight W. The benefits corresponding with the best subset is denoted as B of I and W. Once we have the subproblem definition, we can define our solution to the subproblem. In this case, our recursive formula for subproblems look like below. The running time for this algorithm is big O of n times W because of the double for loop. To understand this algorithm, let's take a look at an example. Suppose W equals 5 and with algorithm above, we essentially fill out a table like following. Each cell in the above table represents B of I and W, and the table looks like above after we executing the first two for loops. We can fill out the table like this and our optimal solution is 7. Now, we have the maximum benefit value given the capacity of the knapsack, which is B of 4 and 5 equals 7. The next question is to find out what items we should put inside the knapsack in order to have this maximum benefit that is 7. The algorithm is seen below. Thanks for watching.